I'm all mixed up about when you want the test. I thought I want the test on Friday, but then I remember telling somebody that we would do it on Monday because it was our longer day.
Yeah.
Did I make that promise to y'all?
I think so.
Yes.
You think we decided to do it on Monday?
Yeah.
Okay, that's what I put on Blackboard, because I'm pretty sure I did say that. We'll put our test on Monday, 1 week from today. That'd be the 26th. And that way, all my tests will be all squished together so that I've got to spend nonstop grading on Monday and Tuesday, but that's not your worry. And it will cover all of chapter 8. And we'll finish probably chapter 9 today, right? Because we have our longer time today, right? Not long time, longer.
Gonna do 4 sections in one day?
Well, we've done 2 of them. We can add and subtract vectors and we can find how long they are, right? But if you'd like to ask me questions about web work on section 8.8 or web work on section 8.7, wherever you are, we're all good?
Can we go through problem 12?
Is that the derivative of,
That's the power series on number 8.8. It's the power series, and it's asking for the first 6 constants in the Mclaren series.
or which, what was supposed to be, you can call it up for me?
It says f of x is going to be equal to 4x squared times e to the negative 10x.
And we don't want to do anything to it, just get it?
It just wants the first 6 constants starting at 0. So the first 6 functions.
First 6 non-zero terms?
No, the first 2 are actually going to be 0.
So I'm making a Mclaren series out of this. So our formula for Mclaren series would be one way to do it. For Mclaren series, we take our function and we find f of 0 plus f prime at 0 times x over 1 factorial plus f of double prime at 0 times x squared over 2 factorial, and so on.
Dr. Patty?
Yes.
It just wanted the first 6 functions of 0.
Okay, so we want the first 6.
So
Okay.
0 through f to the 5th of 0.
Okay, well, I'm going to make then the first 6 terms of this. Right, because f of 0 is 0. But I'm not going to do this by taking derivatives. I don't want to do a bunch of product rules over and over and over and over and over and over and over. We're going to do this with our knowledge of what the power series for e to the x looks like. From that, we're going to write the Mclaren series for e to the negative 10x. And then from that, we're going to get the power series here. So first, e to the x, well, what did that one look like? Well, you can almost do this in our head. All of the derivatives of e to the x are e to the x. E to the x, when x is 0, gives me 1. So every one of these numbers is a 1. So my Mclaren series for the e to the x looks like 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. Let's write out the first 6 terms. So it's 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. So let's stop when we get to the power of 6. And then just say there's more back there that looks just like that. Now to get the power series for e to the negative 10x, we replace each x with negative 10x. square it, 2 factorial. Okay? So we can simplify that if you wanted to do that. I don't know that I want to do it. So the next step is to take each of those terms and multiply them by 4x squared, because multiplication can be done by distributing the 4x squared all the way through there. So that's the next line. 4x squared e to the negative 10x just has a 4x squared written in front of all of those. So here's where I kind of need to know how the problem is stated. Do I really need all of these, or does it want me to stop when I'm at a 6th degree polynomial?
It just wants the first 6 in that series.
The first 6, or does it want the first 6 terms? Is that what happened?
The first 6 terms, I believe.
So 1, 2, 3, 4, 5, I just need one more. And that's the one more. First 6 terms. 6 terms, we didn't have to go that far.
We have wrote this as in like 4x squared and then open parentheses, e to the negative 10x.
Yes. Yes. But I want you to write it in summation form for me. So what would you write? Well, they all have a 4x squared, so that has nothing to do with k. They all have a negative 10x. How's that related to my k? Well, maybe if I start k at 0, I can just put a k up there, right? And then the factorial is the same as the power on the negative 10x. So there's our summation form. Okay. Sometimes it's easy to do that, sometimes it's real hard. This one was just easy. This is how the nature of the pattern that we see. So like one of your problems is phrased, find the whatever derivative of this particular function when x is 0. So let's see how far I've got this going. That last term out there would give us an x to the 7th term. So what if I want to know what is the 7th order derivative of this particular function when x is 0? What is the 7th derivative of this function when x is 0? And the trick is, don't take 7 derivatives of this function. Find the power series representation of this function. Within 7 derivatives, this term is gone. This term is gone after 2 derivatives, right? This is an x cubed, so that won't be around when I'm taking the 7th derivative. This won't be around. The only term that's going to be around when I take my 7th derivative will be this. There'll be terms behind it, but every term behind it will still have an x in it. Agree? If it still has an x in it and I'm evaluating my derivative at 0, those are all 0. So really, all I need to know is to take 7 derivatives of that one term and then let x be 0, but there won't be an x because this is an x to the 7th, right? So we can probably take 7 derivatives of that pretty quick. We can probably take 7 derivatives quicker if I multiplied it out. This is going to be negative 10 to the 5th, which is going to be a negative number. 10 to the 5th, there's 10 to the 1st, 2nd, 3rd, 4th, 5th. Then I got to multiply that by 4. And then I multiply it by x to the 7th over 5 factorial. Now, what will 7 derivatives of x to the 7th give you?
7 factorial.
It'll give you 7 factorial, right? The first one would be 7x to the 6th. The next one would be 7 times 6x to the 5th. If I did that 7 times, I'm going to have a 7 factorial, and the x will now be a power of 0. So the answer to this question is negative 4, 0. How many zeros I got there? 1, 2, 3, 4 more after that. And this will be 7 factorial over 5 factorial. Okay, so there's a problem on your web work like that, that gives you a complicated looking expression and says what is, you know, a large ordered derivative away from that when x is 0. And you got to realize that the lower power terms will automatically have derivatives of 0. The higher power terms in the power series will still have an x. So you'd be multiplying by 0 when you substitute it. The only term that will be left will be the term of that power. You take that many derivatives of that term. Some of you already know which problem I'm talking about. You already done that one? Okay. Did that answer the question, Jeremy?
Mhm.
Anybody else have something? Yes, sir.
Can you write the first 4 non-zero terms for f of x equals t squared sine of 5t for the tangent series?
T squared sine of 5t.
Yes.
And how many terms? First
4.
4 non-zero terms. Okay, so was the sine an even function or an odd function? You remember?
Odd.
Sine is odd. So for instance, if I want to write the sine of x, I'm going to get odd powers on the x. Does anybody remember that it's an alternating series? And then underneath those x's, we have the factorial by whatever power it is. So my first would be what? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. There's 4 non-zero terms for the sine of x. Now let's replace each x by 5t. So now the sine of 5t look like 5t minus 5t cubed over 3 factorial plus 5t to the 5th over 5 factorial minus 5t to the 7th over 7 factorial. And now my last step is to take those and multiply each of them by t squared. So let me actually do the multiplying. This will give me a 5t cubed here, minus 5 cubed, that's a t cubed times a t squared, gives me a t to the 5th. That'll be a 5 to the 5th. T to the 5th times a t squared gives me a t to the 7th. And then I'm going to have minus 5 to the 7th, t to the 9th over 7 factorial. Okay.
Will the test on Monday be in person or online?
In person. In person. We'll try it together. I'm gonna try to grade things on paper and grade things on the computer. What else? Y'all good? How many do you want?
One question.
One question.
Yes.
Write the power series for this, find the interval of convergence. Use it to evaluate whatever, the interval from 1 to 2 of this function. One question with parts? Parts A through Q, like my stats test in grad school? I don't know, I'll think more about, I put a review on Blackboard and I'll think more about how many questions, about the same length as the other ones, right? Except these are quick. Anything else? Okay, so everything you want to know about vectors. Everything you want to know about vectors. What do you want to know about vectors? Let's put some stuff up here and see where you know it. That's integration by substitution. That's what calculus one. There you go. There it is right there. Okay. So here's a vector in 3 dimensions. So technically, this is section 9.2, where we talked about vectors in 3 dimensions. Our 3 dimensions are x, y, and z. Where the y and z axes correspond to the plane that's the board. There's the y-axis, there's the z-axis, and then the x-axis is coming out here. So the x-axis is coming out this way. And going back into the board for the negative x-axis. Positive z, positive y, positive x, back there's negative x. So if I kind of try to draw that, looking like it's coming out of the board, looks like it's coming out, something like that for our x-axis. So our vectors in 3 dimensions can be written in terms of the unit basis vectors I, J, and K, where the vector I is the vector now that has a 1 in the x position, but 0 elsewhere. J has the 1 in the y direction, but 0 is elsewhere. And K looks like 0, 0, 1. So these are called the unit basis vectors in R3. You'll learn in linear algebra that a basis for a space is like the building blocks. All vectors in the space can be written as some linear combination of those. So if I have the vector 4, 2, -5, in terms of the basis vectors, I can write that as 4 times I plus 2 times j minus 5 times k. From the, if I were to draw this standard position vector, I would have to pin the tail at 0, then come out 4 units in the x direction. So I'm coming out this way, 4 units in the x direction, but I come down here. Then I go to the positive y 2 units. So from here, 1, 2, and then in the z direction, 5 units. 1, 2, 3, 4, 5. So it would look something like that. Coming out, move it over, and then going down. But you still do things to these vectors component-wise, like for instance, I can take that vector and I can add the vector, say 1, 2, 3. Vector addition is done component-wise. So I get another vector whose components are 5, 4, 2. I subtract things component-wise, and I multiply by a scalar's component-wise. So if I have 2 times this vector minus 5 times this vector, and I can do that in a sequence of steps and get the vector 8, 4, negative 10 minus the vector 5, 10, 15. And then we subtract component-wise. 8 minus 5 gives me a 3. 4 minus 10 gives me a negative 6. Negative 10 minus 15 is negative 25. So things are done component-wise in terms of addition and subtraction and scalar multiplication. Then if we call this vector, say vector v, and I wanted to know its length, then we just do the 3-dimensional version of the Pythagorean theorem, where this is the length of the hypotenuse. So we take leg squared plus leg squared plus leg squared, where these guys are the legs. So I would write that as 4 squared plus 2 squared plus negative 5 squared, and then to get the length, we take the square root of it. And so we have 16 plus 4 plus 25. So what is that? 45? You like simplifying. 45 is 9 times 5. 9 is a perfect square, so I can write that length as 3 square roots of 5. Okay? So addition is done component-wise, subtraction is done component-wise, scalar multiplication component-wise, and the magnitude of the vector whose components are A, B, and C is the sum of the squares of the parts. What if I want a vector in the opposite direction of that vector v that I have down there, 4 to negative 5, with a length of 10. Find me a vector whose length is 10, but has the opposite direction as the vector whose components are 4, 2, and negative 5. Firstly, given a vector pointing this way, how do you get a vector pointing that way?
Switch the signs.
Switch the sign, multiply by negative 1. So just multiply that by negative 1, and it changes the other direction, but it hasn't changed its length. How do I make it have a length of 10? Well, I do it in 2 steps. First, I make it have a length of 1. Given any vector, how do you find a unit vector of that same direction?
Divide each component by magnitude.
Divide each component by the magnitude. So if I divide each component by 3 square root of 5, I get a vector of length 1. Now I want to turn it around, so I change the sign. And now I want to make it length 10, so I multiply it by 10. How's that sound? So we just want 10. Now we get to take our unit vector, 3 over the square root of 5. Now we turn it around, and then we multiply it by 4, 2, negative 5. Right? This makes it length 10 after we make it into a length of 1. Right? V divided by the magnitude of V is equal to a unit vector in the same direction as V. So get in the same direction by dividing each component by its magnitude. Turn it around by changing the sign. Make it length 10 by now multiplying by 10. You can leave it out there, you can stick it inside, doesn't matter to me. Is that too easy? Let's see, that's in 2 dimensions. That's in 2 dimensions. All right, so let's go plot some points in 3 dimensions. Let point A have coordinates 1, negative 2, 3. Point B have coordinates 4, 1, 0. And point C have coordinates 3, 5, and 2. So these are 3 points. A, B, and C would be 3 points in R3. So in part A, I want you to plot them. In part B, let's see if you can find the distance between points A and B. And in part C, I want you to write the 3 vectors. Vector AB, vector AC, and vector BC. Let me see if you can plot those points first.
Is positive x towards us?
Yes, positive x is towards you. So that's what I drew that cube over there for. Let me draw it big over here. Let this piece go over here. Maybe this helps you visualize the coordinates. Put the origin right here. That's the origin. The origin of that corner. I didn't draw it so pretty, but there's the z-axis. Here's the y-axis. And here's the x-axis. And maybe that looks more like it's coming out at you. I put my three-dimensional quality on there. Did you bring your 3D glasses to class today? How do those even work? How do they make you see in 3D? Okay, plot them. So A is 1, -2, 3. So let's say that that's 1 unit. So I go out 1 unit there, and so from here, I go in the y direction, -2 units. So there's 1, 2, and now from here I go up 3. 1, 2, 3. All right. The next one. I go out 4 units, so that was 1 unit. So 1, 2, 3, 4. From here I go 1 unit in the y direction and no units up or down. So here's point B. All right, the next one I have to go back. So I go back in the z direction, I mean the x direction, 3 units. So 1, 2, 3. Now from there in the y direction, 5. 1, 2, 3, 4, 5, and up 2. 1, 2. And so there's C. Okay. Okay. How do you find the distance between points A and B? If they were in 2 dimensions, we make that right triangle, we find the sum of the square of the legs, and then take the square root. What do you think you do it in 3 dimensions?
Could you add the distance between like each component? Like they're 3 apart x, and then
So in 2 dimensions, if you had x1, y1, and x2, y2, that's point P and point Q. The distance between point P and Q was how far the x's were squared plus how far apart the y's were squared, and then take the square root sign. What do you think you do in 3 dimensions?
same thing, just add the z.
Yeah, you just add another z2 minus z1 squared. So make it more general. Doesn't matter which order you subtract them because we're squaring it. So you don't even have to be consistent down the line. In general, the distance between 2 points is how far apart their x's are squared, plus how far apart their y's are squared, plus how far apart their z's are squared, added together, and then take the square root. So for the distance between A and B, there's my square root sign. Let's see, I can go with 4 minus 1 all squared here, plus 1 minus a negative 2 all squared here, plus 0 minus 3 squared here. So this gives me 3 squared is 9. That's another 3 squared is 9. And that's another 3 squared is 9. So I get the square root of 27. Or 3 square root of 3. Okay? How did we find vectors through 2 points in R2? How did we get the components that go in here?
You just find the distance between each component.
Well, we had to do it in a particular order. Take the coordinates of B and subtract off the coordinates of A. So this first component would be, for AB, we have 4 minus 1. And then 1 minus a negative 2. And then 0 minus 3. So vector AB looks like 3, 3, negative 3. All right, let's see if you can finish off AC and BC real quick. The order is important. Terminal point minus initial point. All right, so we'll catch up with you. You take the coordinates of C and subtract off the coordinates of A. So negative 3 minus 1, 5 minus a negative 2, and 2 minus 3. Gives me the vector minus 4, 7 minus 1. Right? Okay, BC. Take negative 3 minus 4. Um, 5 minus 1. And 2 minus 0. So we get negative 7, 4, 2. Was all okay? Okay, so for part D, here's what I want you to do. Find the magnitude of those 3 vectors that you have. Magnitude of AB, magnitude of AC, magnitude of BC. So the connection I want you to see is that the distance formula between 2 points is the same as the magnitude of the vector. Because to get the components of a vector, you subtract. To get the magnitude, you square the components, add them, and take the square root. So it's still the same interpretation in 3 dimensions. It still gives the length of the hypotenuse, or in this case, the vector between 2 points. So AB we already have, 3 squared plus 3 squared plus negative 3 squared under the square root sign, which we wrote as 3 square roots of 3. AC will be a negative 4 squared plus 7 squared plus a negative 1 squared. So 4 squared is 16. 7 squared is 49. 1 squared is 1. So 50, 66 squared is 66. I don't think I see any perfect squares in there. BC has as its length negative 7 squared. I'm going to go ahead and just put 49. 4 squared is 16. 2 squared is 4. So 20 plus 49 is the square root of 69. Okay? So the magnitude is essentially the distance formula. The distance formula is the magnitude. You know what else the distance formula describes? It describes the set of all points in space that are a fixed distance away from a center. If we're in 2 dimensions, and I have some center here, and I hook a string on that of length r, and trace out all points that are r units away from that center, I get a circle. So now let's do that in 3 dimensions. Here's a point in space with a length of r, and I'm going to trace it out that way. I'm going to trace it out that way, all the radial different directions around from that center. And what type of 3-dimensional surface am I describing? A sphere. The distance formula gives us the equation of a sphere that is exactly r units away from the center whose coordinates are h. I'm going to think of some a, b, and c. Let's say a, b, and c. So let's talk about some graphs in 3 dimensions. Get away from vectors for a minute. Set of all points in space in R3 that are r units away from the point whose coordinates are a, b, and c, describes a sphere. And so if I let x, y, and z be the coordinates of the random point in space, a, b, and c is the other point, then use the distance formula. I know that my distance is equal to x minus a squared plus b minus x minus b squared, y minus b squared, plus z minus c squared, and now I want them all r squared units away. So that's what it looks like to have a sphere in 3-dimensional space with center A, B, and C. So here's an example of a sphere. X squared plus y minus 2 squared plus z plus 5 squared is equal to 9. Describes a sphere whose center is, you need the ordered triple for the center, and whose radius is Give me the radius. So here I describe my center as ABC. So x minus a, y minus b, z minus c. Gives you a center of ABC. It's as if you took what's in here and set equal to 0 and solved for x, y, and z. So if there's not a number taken away or added to the x, then the x coordinate of the center is 0. What's the y coordinate of the center? And then the z coordinate? And then the radius? Very good. Now let's go the other way. Yeah, that's too easy. If I give you the point and the radius, you can fill it in too easy. Let me give you one that's multiplied out and ask you the same thing. Let's take x squared plus y squared plus z squared plus 4x plus 6y minus 2z is equal to I'm then going to come up with a pretty number, so tough luck.
$61.
Let's try that. I'll try 69 over there, but I make no guarantees. Take that equation. How do I know, other than I'm like a math goddess, that that's the equation of a sphere?
Because you have all three components.
This is the giveaway that it's a sphere. As soon as I put different coefficients here, then I take my sphere from being a perfect sphere to making it an ellipsoid. So if I had an x squared plus 2y squared plus z squared, it's not a sphere anymore. It's got a football shape. But since all the coefficients are the same, I should have a sphere. Your job is to complete the squares to tell me what the center is and what the radius is. So complete the squares. Find the center and the radius. Remember how to complete the squares. You think you got it? I'm going to shuffle furniture here. I'm going to put the x's together. So I'm going to move the 4x over here. And then I'm gonna leave a gap to add a number. Do the same thing with the y's. And I'm gonna add a different number. And then I'll do with my z's. Add a number there. And then I gotta balance the equation, so whatever numbers I add there, I have to add here, here, and there. Add the same thing to both sides. Right? And the number we always add is 1/2 the middle term squared. So half of 4 is 2, 2 squared is 4. Half of 6 is 3, 3 squared is 9. Half of 2 is 1, 1 squared is 1. We're always adding. But now the signs play a role in how we factor it. All the factors have this sign in between. So x plus 2 all squared. It's got all pluses, so this will be y plus 3 all squared. And then the last one's going to be z minus 1 all squared. And let's see, here I have 69, 70, 79, 80, 81, 82, 83. So I didn't do my arithmetic in the head. I tried to get 81 and I added it off by 2. Foo, I should have gone with 67. Is that what you got? So my center is, give me the coordinates.
-2, -3, 1.
And my radius is just the square root of that number. Everybody get that one right? Then I guess you deserve a break. We'll take a little 5 to 10 minute break. 7-minute break. Take a 7-minute break. And then we'll continue with graphing in 3 dimensions. You guys at home need to ask anything, or do you need a break as well? You're just laying there on your bed, doing a math class. You forgot?
No, I forgot, but I remember.
It's in there somewhere. Okay, 0 for 1,
Yes, please.
0 for 2. Ah, $25?
Oh?
That's you $1,
Is that a wager?
but I get to stand in front of the trash can.
No, I'm not allowed to gamble.
It's not gambling if you know you're gonna make it.
$25, did I miss it?
Oh.
Damn it, that's pretty sad. But I'm out of practice because I haven't eaten out of non-chocolate. Out of practice. Here's my other teacher trick. My chalk right there.
Oh.
I had to teach that to my sons when they started Little League because I was afraid they'd be sitting on the bench with nothing to do. So I showed them how to do that with a baseball. I bet they don't even remember it. They just think, oh, that old mom, she thinks she showed us everything. Whew. Mondays are hard, aren't they, Travis?
Sure.
They're hard.
I think I woke up like 30 minutes ago.
Did you? What time did you go to bed?
God, 4 a.m., I think.
I almost went to bed at 4, not. My husband said, hey, let's watch that PBS documentary on Ernest Hemingway. Man, nothing is more soothing than a PBS documentary. Boom, I was out. I had a glass of wine in my hand. I was out. I know I'm supposed to be watching that and enjoying it, but
Too boring.
they picked the narrator with the soothingest voice. Let's see. What's next? Will the final be online or in person? Does anybody know? When is our final?
The 11th.
I don't know. What is the 11th? Last day, huh?
Mhm.
I'll let you guys decide that. But our next test is in class. Exam 3 is in class on the 26th. Yes, sir.
How does the final count toward our final grade?
Okay. Let me see if I remember. Let me see that. Tired of this stupid thing. Okay. Let me see if I remember how we did this. Each test is 20%.
You can make money.
Final
Or you could try.
is 25%. So that means your write-ups plus your web work is remaining 15%. That's how your grades figure. 25% on that whole final. So they got together and wrote the final on Friday night at 6 o'clock. Well, I couldn't join them because I had to be at a dinner on Friday night at 6 o'clock. So I have no input on the final. But it'll look good. It'll be pretty. I trusted them. Who gets together on Friday night at 6 o'clock to write a final?
Not me.
It wasn't me either. You all back? Missing anybody? You all back? Okay. So sphere in 3 dimensions has all 3 variables squared and added together with plus signs in between. Anything that was a line in the XY plane, so picture my desk as the XY plane, and then the Z-axis coming up here. So if I've got a line in the XY plane, it extends infinitely in the Z direction. So that line becomes a plane. A line in 2 dimensions, as its equation mx plus b is equal to y, is a plane in 3 dimensions. It'll be a plane, that particular one, which would be perpendicular to the xy plane, but we can make planes in any direction, slanted, by writing an equation with first degree variables in x. So in general, an equation that looks like a times x plus b times y plus c times z is equal to d, where a, b, and c and d are whole numbers, is the equation of a plane. In R3. So for example, x plus 4y plus 2z is equal to 6. X plus, what I say, 4y plus 2z. I won't put a 6, let me put a 16 out here. X plus 4y plus 2z equals 16 is the equation of a plane. And I'm going to draw this plane by drawing where the lines and where this plane intersects. The xy plane, the zy plane, and the xz plane, like this. So here's my z-axis, there's my y-axis, and then in my cube, this is the x-axis. So if y and z are both 0, this is going to cross the x-axis when x is 16. So let's put the point 16, 0, 0 right there. When x and z are both 0, that means it has a y-intercept of 4. Put 0 in for x and z, solve for y, and you get y as 4. So if that's 16, 4 is about here. And then when x and y are 0, z is going to be 8. So if that's 4, then that's 8. So that plane has these, that's called the trace of the plane in the XZ plane. Here's the trace of the plane in the YZ plane. And here's what the plane intersects the XY plane in that line. So when I draw that little triangle, imagine now that those pink lines extend infinitely, so that forms the plane. I just draw it by drawing the traces of the graph in each plane. Okay? So colored in solid, so it's kind of sitting out there, catty corner to the corner of the classroom or something. Okay, but there's no boundary to a plane that extends infinitely in every direction. And I just plotted all the intercepts by finding what goes in for X, Y, and Z when the other two variables are 0. Yes?
You said that's just like the quantum plane that intersects like the three lines?
The 3 planes. The YZ plane, it intersects the YZ plane here,
Oh.
intersects the XY plane here, intersects the XZ plane here. Okay, so now let's look at the line Y is equal to 2Z. Well, you think it's a line, but it's not. That's a plane. Y is equal to 2Z is a plane in R3. So here's the Z-axis. Here's the Y-axis. X is coming out at you. I put that in last. If Y is 2Z, and I just draw this in 2 dimensions, then when Y and Z are 0, then I get 0. When Z is 1, Y is equal to 2. So here's that line in the YZ plane. Now let's make the X-axis come out here. And now I draw that plane parallel to the X-axis. So it looks something like that. Right, it's coming out at you. Any first degree equation in all of your variables or some of your variables is a plane. What is this equation? What is that in the XY plane? It's a circle centered at the origin. What do you think that looks like then in 3 dimensions?
A circular plane.
Here's Z, here's Y, there's X. I've got this circle here. Intersects at 0, 4, 0, 4, 0, 0, back here at -4, and back there at -4. But the absence of the Y variable means that this extends infinitely up and down. Pair it with the Y-axis center in that thing. So a circle in one plane becomes a circular cylinder in R3. A cylinder is going to be the general name of any surface in 3 dimensions, whether it's closed or not. Here the cross sections are circles, so we can say they're circular cylinders. But if I draw, say, the graph of Y is equal to the sine of X in the XY plane, then extend that infinitely in the Z direction, then we say that that surface generated is a cylinder. It's just not a closed cylinder.
Quick question.
Yes.
So when a variable isn't included, it's presumed to be stretching out infinitely? Is that correct?
Because that holds for every Z. I drew it down here for Z is 0, but it holds for Z is 5, it holds for Z is 20, it holds for Z is -2. So it goes the entire up and down the Z axis.
Okay.
Okay,
You
yes.
said every shape in the. Can you explain a cylinder?
If a cylinder is going to just be a general name for a surface in 3 dimensions, whether it's closed or not. So if you picture on the floor the graph of the sine curve. That's the XY plane. Now Z's going up this way, so you've got a piece of three-dimensional metal maybe coming out looking like that. That will be called a cylinder, even though it's not a closed or circular. Yeah, sorry. Because what else would you call it? A big old sign sheet?
Yeah, I don't know.
One of the things that you're going to do in Calculus 3, like your first week, is you're going to be given the 3 points that are the points of intersection and asked to come up with the equation of the plane. That's a little harder to do than come up with the equation of the circle. Because one of the things that characterizes in 2 dimensions, something that characterizes a line is its slope. Something that characterizes a plane is some version of its slope. If my piece of paper represents a plane, well, there are infinite number of lines I can draw that are contained by that plane with different slopes, right? So we don't use the slope of a line in the plane to describe the plane. We use something called a vector that's normal to the plane. So it's a vector that makes a right angle with every line in that plane. Once you know the vector normal to the plane, then it's easy to write the equation of the plane. Normal means perpendicular. So you've got to work with vectors in that case. So that's why we're going to go back and start talking about vectors again. Okay? Now, writing an equation of a line in 2 dimensions is a lot harder because, if a line's in the plane, really all you need to know are the x and y intercepts. But what if the line is in space? Right? It may not intersect any of the coordinate axes. So you're going to need to describe a line in space based upon something called its direction vectors. What direction is it pointing in the x direction? How is it pointing in the y direction? How is it pointing in the z direction? And so you'll need to know things like that, direction vectors, in order to write equations of lines in 3 dimensions. In 2 dimensions, if you have lines in the xy plane, 2 things can happen. Lines intersect or they don't. But in 3 dimensions, they can intersect, they can be parallel, but then they can be non-intersecting and non-parallel. So you'll be able to tell those quantities, intersecting, parallel, or skew, by looking at the direction vectors of the line. I wish I got to do Cal 3. Makes me miss it. Forgot how to do it, but let's see if there's anything else I need to tell you on that. That's okay, that's okay. Did that, did that. Did that. All right, I did all of those. Okay, so let's get back to talking about vectors. I've got 2 more vector operations to show you. And they're true versions of multiplication. There we go. Right there. We're going to have something called a vector dot product. So let's let vector V be a vector whose components are A1, B1, and C1. And vector W have as its components A2, B2, C2. Move that over. The operation V dot W is an operation that produces a scalar. It takes 2 vectors and it yields a scalar. By multiplying the 2 x components together Then you add to it the product of the two y components. Then you add to it the product of the two z components. So it gives you a scalar. Scalar operation. So for instance, let's take the vector, let's see, B to be the vector 1, 2, 3, W to be the vector -1, -5, 4, Z, I don't want to use a Z, BWS to be the vector 0, 3, 2. Then V dotted with W. V dotted with W is the scalar 1 times -1 plus 2 times -5 plus 3 times 4. So I get -1 minus 10 is -11. -11 plus 12 is +1. So now it's your turn. V dotted with S. You get 12? V dotted S. 1 times 0 plus 2 times 3 plus 3 times 2. So 6 plus 6 is 12. All right, how about W dotted with S? You're -9? No? -15 plus 8. -15 plus 8 is -7. -1 times 0 plus -5 times 3 plus 4 times 2. So -15 plus 8 is -7. Okay, how about V dotted with V?
Just out of curiosity, why are we calling it multiplying? Like multiplying, like, again, or is like dotting like a different?
Dotting is the name of the operation, because we're going to have an operation with a cross in between, and we're not going to call either one of them multiplying.
And this is called vector.
Vector dot product.
Vector dot product.
There was this guy named Vector Dot.
That's the actual name of.
So V dotted with V looks like 1 times 1 plus 2 times 2 plus 3 times 3. Or 1 squared plus 2 squared plus 3 squared. Does that remind you of any operation? Where do you have a 1 squared plus 2 squared plus 3 squared? That's part of finding the magnitude. If you dot a vector with itself, it's like taking the magnitude of the vector, but without the square root sign. Dot any vector with itself and you get its magnitude squared. So I get 9 plus 4 is 13, I get 14. So the magnitude of this vector is the square root of 14. All right, here's something else that the dot product is good for. Let's see if I can remember how this goes. Suppose I'm in 2 dimensions. Don't worry about 3 dimensions. Here's a vector V in standard position and a vector W in standard position. In 2 dimensions, I can figure out the angle theta between 2 vectors because I took trig. And I know how to find the angle between the angle in any triangle. Right? If I make a triangle out of this, if I draw this vector with its tail at the tip of W and its head at the tip of V, what's the name of that vector?
WV.
Remember that
Oh,
in the parallelogram rule, this vector was W plus V. This vector was V minus W. That's this one. How long ago was it since you've had trig? And you were asked to find an angle measure in a non-right triangle. Right? I can't use sine, cosine, tangent when my triangle's not right. This is called an acute triangle, because all the angles are acute angles. And for acute triangles, we have something called the law of cosines. Once upon a time, you knew the law of cosines. Can you fake it? Let's put some A's in here and B's and C's. So A, B, C. So suppose I want to know this angle here. Well, I could figure out the cosine of that angle. Cosine of that angle that corresponds to B is equal to, let's see, let's name the sides opposite the angles with lowercase letters. That's a little a. That then would be little c. And this over here would be little b. Okay, so this is the angle included by those 2 sides. Then I square each of the sides that it's included by. And then I do something else. I subtract. I forgot what I subtracted.
2AB cosine C.
Yeah, so I forgot how to do it. What was it? Say what?
I understand why would you make the right triangle?
Because it's clearly not a right triangle. You see?
No, but you can make them other 2 in the right triangles and then you figure out where you at from there.
What do you mean?
Never mind.
Then you gotta know something called a vector projection. Do you know it?
I'm just saying, it's an awful lot, like they could be coming from
I
somewhere.
forgot my law of cosines.
I think it's 2AB.
No, I think you're right. Let me put it this way.
Yeah, let's do it.
That's the included sides. This
Yeah.
side, b squared.
Figures.
B squared is equal to c squared plus a squared minus 2ac times the cosine of that angle b. That's it.
We figured it out.
That's the law of cosines. Whew. What does that have to do with my vectors here? Okay, my length here, this is at the origin, this length is the magnitude of vector v. This length is the magnitude of vector w. And so this length is the magnitude of v minus w. So according to what I wrote down below with that triangle, then the magnitude of v minus w is equal to the magnitude of v squared, all my magnitude squared, plus the magnitude of w squared minus 2 magnitude v times the magnitude of w times the cosine of the angle in between. So here's the law of cosines with vectors. V minus w squared is equal to v squared plus w squared minus 2. Oh, I take that back. I'm gonna leave it. Magnitude of V, magnitude of W, times the cosine of the angle between vectors V and W.
Can you just agree not to put that on a test?
What? No, because I wanted to simplify it and make it look like a pretty formula. It's gonna look like this. So I was gonna put some coordinates in here, and I was gonna find these vectors in terms of their coordinates. But I was gonna do it algebraically. I was gonna call the coordinates of V that, the coordinates of W that, so the coordinates of V minus W will be A1 minus A2, B1 minus B2, C1 minus C2. So I was going to use those letters. I'm going to compute their magnitudes by squaring them components. I was going to multiply them all out, collect like terms, and then out comes a formula. So here goes that part. It's a lightning bolt. If you don't want to watch me do that, I saw your eyes roll back. Here's the explosion. Sparks are flying everywhere. And out comes this formula. Between two vectors, the cosine of the angle between two vectors is going to be a number. Not just any number. It's going to be a number between -1 and 1, right? That you get by taking V dotted with W divided by the magnitude of V times the magnitude of W. But I so wanted to prove it until Cole rolled his eyes in the back of his head and made that comment like, don't put this on the test. We took all the fun out of the math teacher part.
How long would it take to prove it?
It'd take about 15 minutes because I got to do lots of, right? Do lots of dot products and binomial expansions.
I
And,
apologize.
so you're just going to have to believe it. It's in your book if you want to peruse it. It's kind of like your version of the Ken Burns Hemingway documentary. Okay, well, let's use it. Let's use it. It works also in 3 dimensions, right? So if I wanted to find, let me use prettier numbers though. Find the cosine of the angle between, I know it's going 2 dimensions, and let's look at some position vectors. That vector, whose terminal point is at 1, 3. And the other vector, whose terminal point is at 4, -2. So vector V and vector W. Find the cosine of that angle right there.
That's what I was saying, I don't want to get a party pooper or anything, but that does look like awful lot like you can make 2 right triangles out of that, you don't have to do all the extra math and stuff.
Where's the right triangles?
I mean, that's all I'm saying, you know, like you got 2 vectors right there, they're so closely lined up to those beautiful little, like,
Here?
yeah, like the Y
And then
axis
here?
and the X axis, you know, you can make some right triangles and then figure out.
But how do I know what that point is?
Well, I mean, all I'm saying, you know, all I'm saying is it does look like you could make some
It
right
does.
triangles out of it if you have like the
Okay.
magnitude,
And
whatever.
I'm going to give that to you in a minute when I
That's
talk
all I'm
about
saying.
projection
I mean, you
vector.
got it, like, I mean, I'm not saying anything, I'm not smart by any means.
Finding the
All I'm
coordinates of
saying
this is difficult, and
It's
you need
like-
another dot product.
Like, there's a lot of people out there that are gonna do this math and stuff, I just don't plan on being one of them, you know what I'm saying?
So this is just the hazing part of your education.
I'm saying is that if you have a ruler, I can tell you exactly how long those are, find out how the cosine in just a couple seconds.
That's all I'm saying.
But my problem is, I'm not gonna have a ruler that helps me out when I'm in three-dimensional space
Oh,
or
no, you got
n-dimensional
that one, you got
space.
that one, you can take care of that
So
one.
if we can do it in 2 dimensions, we can do it in 3, 4, 5, 6 dimensions.
I just don't want people thinking I'm sitting here being a kook all that, like. sound.
Nobody in here thinks he's a kook.
Whatever.
I hear it.
That's a good plan, but again, when you don't have position vectors, the way I've drawn these, you just got some vectors in space, finding where these things intersect the coordinate axes involves something called a projection vector. So if you've got a vector in 2 or 3 dimensions and maybe the sun is shining down on it and it drops a perpendicular, the projection of that vector on that plane has a name and has a dot product way of finding it. But you're right, it looks like it would be a very easy thing to do, but when you're in many dimensions and when you're not doing position vectors, it's not that easy. But it is easy if you just do a dot product. Dot products are super easy. Magnitudes are super easy. All right, so all we have to do is write this vector v as a position vector. So I went over 1 and up 3, to the right 1 and up 3. And for vector w, I went over 4 and down 2. And now I can use that magically produced formula that you wouldn't let me derive and say the cosine of that angle between those vectors is their dot product. And then make sure we get a number between 1 and -1 by dividing by their magnitudes. So quickly, what's the dot product between V and W here?
-2.
It's -2, right? 1 times 4 plus 3 times -2. So the dot product is 4 minus 6 is -2. All right, then the magnitude of V is 1 squared plus 3 squared, so it's a square root of 10. The magnitude of W is 4 squared plus -2 squared. So what I say, square root of 10, 16 plus 4, square root of 20. So it's -2 divided by the square root of 200. And so it's -2 divided by 10 square root of 2. That's the cosine of angle theta. If I wanted to know the angle, I'd have to specify whether I wanted the angle in radians or degrees. So some of your homework problems asks for it in radians. Some asks for it in degrees. Calculus is done in radians. So if I just take the inverse cosine of this number, that's in radians. How do you convert an angle from radians to degrees?
Radian.
Look it up.
Pi over 4 radians. How do you find that pi over 4 is 45 degrees?
Multiply by 180 over pi.
Multiply by 180 over pi. So if you were asked for this angle in degrees, it's the inverse cosine of that number times 180 over pi. That's some high-powered math we're doing today.
Oh, yeah.
So pay attention when you're doing your web work, whether it wants radians or degrees. If I do the inverse cosine, it's in radians. If I multiply by 180 over pi, it's now in degrees. Okay, so now let's look at the projection vectors. See if I have that in my head. Let me see if I remember how to define the projection of one vector onto another.
Are we still at 9-2?
I think this is, and the dot product is in 9.3.
Okay.
9.2 was just vectors in 3 dimensions. So I think all this is in 9.3. I think. The dot product is 9.3, the cross product is in 9.4. So
We're gonna say that for another time.
the cross product, was that a request or was that a question? I mean, don't give me all this good stuff in one day.
Bro, he put in that work trying to get you not to do stuff.
Oh, yeah.
Everybody understands how we're doing it in physics?
I understand it better now we're in here. though.
You're doing dot products in physics?
Yeah.
Give me one of your applications for dot products for physics.
We have a
Here's-
chapter.
Work.
Here's vectors. Do a
Work
cross
is-
product for the
Work is a
vectors.
dot product. Work is a dot product. If you've got, work is the force vector. So if we take an object and move it from point P to point Q by applying some force on that, and it moves the object from point P to point Q, work is the dot product of the force vector and the vector formed from point P to point Q, right? So that's not hard, right? So if force F, which is 2I plus 3J, acts on an object in the XY plane and moves that object from point P, which is up there on the y-axis at 0, 2, to point Q, I don't know, 5, 10, then work done is a scalar. See if these folks can see that. Yep, they can. The work done, according to what you learned in physics and what, I mean, everybody knows this one. Work is force times distance, just like it was back in chapter 6, right? But now they're vectors, and our version of times is going to be the dot product of the force vector and the vector that describes the motion. So we first get the vector that describes the motion. From P to Q gives me what vector in IJ notation? Five I
Plus 8J.
plus 8J. Coordinates of Q minus coordinates of P. 5 minus 0, 10 minus 2. Yes.
So these don't have hats on them? What do the hats mean again?
Oh, the hats just keep you from thinking they were ordinary variables,
Oh, okay.
right? So when you put the hat on, they make them those basis vectors. And so in our problem, work is equal to the dot product of these, 2I plus 3J dotted with 5I plus 8J. And so I have 2 times 5 plus 3 times 8. So I have 10 plus 24. I have 34 units of work. I didn't specify what units of force and distance were, so I'll just leave that vague.
Does the dot tell you anything about like parallel or perpendicular? Because like the force has to be parallel. Like in
It
order.
does. Look at our law of cosines. Look at our law of cosines. We put it over here. What if our two vectors v and w were perpendicular, so that the angle between them is a 90-degree angle? What's the cosine of pi halves?
0.
0. So if this is 0, the only way this is 0 is if the dot product is 0. Two vectors are perpendicular if and only if their dot product is 0. They say orthogonal when they talk about vectors. And only if their dot product is 0. Zero the scalar, not zero the vector. Dot product is always a scalar. V dot W is 0. So there's the quick way of saying that. V dot W is 0 if and only if V is perpendicular to W. Yes, sir.
Orthogonal is the three-dimensional version for perpendicular.
Yeah, it's general, more general, but orthogonal means perpendicular.
So like all dimensions do,
Say again, please.
like all dimensions, like. if
Yeah.
you-
That's because there was this guy way back, his name was Orthogonal. That's that history of math class that I took.
Is there like a Thomas math out there somewhere?
The Thomas math,
We have things like Pythagorean, it's not exactly that far of a stretch.
that's right. That's right.
Pythagorean, whatever his name is, I don't know.
I'm just waiting for that Ken Burns documentary.
Where's Mr. E?
Okay, so let me see if I can remember this, because I left my notes on my desk. Here's a vector V. And here's a vector W. There's a vector called the projection of vector V onto vector W. And it's this vector. If I drop the shadow down here and make a right angle, it's this vector that is parallel to vector W. Right there, it's drawn in pink. Now, I told you what it looks like if two vectors are orthogonal. Two vectors are parallel if one is a scalar multiple of the other. The way we write the notation for the projection of V onto W is we abbreviate the word projection. We put the vector that we are projecting, and we put the onto vector down here. Now let me see if I can remember how to do it. Let's see.
What's the projection, the little?
The pink vector right there. So it's the adjacent side to this angle theta. And that's a right triangle. So I know the cosine of that angle theta is equal to this projection vector length divided by the hypotenuse length. So if I just call that projection of V onto W, gosh, I don't know what to call it. Let's call it P. So I don't have to write that whole thing. So I have from that picture that the cosine of that angle theta is going to be the length of P divided by the length of V. Right? So what does that got to do to tell me about P? P is going to be that number, this number, magnitude of V times the cosine of theta gives me the length of P, right? That's the scalar multiple of W that is the projection. So the projection of V onto W is, I take vector W, I make a unit vector out of it. So now this is a vector in the same direction of W, but it's now a unit vector. So it might be here. And now I stretch it out by this amount. So I stretch it out by multiplying it by this scalar, magnitude of V times the cosine of angle theta. But the cosine of angle theta from our formula up there, let me see if I've got this in their picture. Yes, I don't. Keep it all a secret from you guys. There it is. Okay, so I said the projection was this little pink vector, which is going to be some scalar multiple of W. To figure out that scalar multiple, I do the right triangle and said the cosine of that angle by right triangle trigonometry was the length of the adjacent side divided by the length of the hypotenuse. So the cosine of that angle is the length of the adjacent side divided by the length of the hypotenuse. So if I solve it for the length of vector P, I get magnitude of V times the cosine of theta is the length of P. That's the scalar multiple of the unit vector in the same direction of W that will give me that vector called P. So there's the unit vector. Then I've got the magnitude of V times the cosine of theta. And then I need to multiply it with this vector W. So let's replace cosine of theta now. In terms of these, it should be V dot P divided by the magnitude of V, magnitude of P. So I'm going to put that in right here. So I have that the projection is equal to vector W divided by its magnitude. Then I multiply it by the length of vector V. Then the cosine of that angle was V dot P divided by I don't think I care about P. I'm going to use W here because it's a vector on that side. That's what I want. I want the W. Divided by the magnitude of V, magnitude of W. Now the magnitude of V will cancel because there's one down here and there's one up there. This is a scalar, and that's the magnitude of the vector. So my final formula looks like this. The projection of vector V onto vector W is equal to V dot W as a scalar, that scalar, times vector W, and then it's divided by the magnitude of W squared. There's that formula. So this is a scalar, this is a scalar, so all of this is a scalar multiple of the vector W. That scalar that we have in front of W is called the component of vector V onto W. The component of V onto W is given by this mess here, V dot W divided by the magnitude of W without a square. The square part sticks with the unit vector W. So for instance, if I have vector V to be 2, 3, and vector W, let's just use my vector over here, 5, 8. See if I can see that. I can't, of course. There's our formula at the top. And if you put one of these with W, you got a unit vector in the same direction of W. Everything else that's left is called the component of V onto W. So given those two vectors, find projection of vector V onto vector W. So to help you remember the formula, it's the dot product between the two vectors. Then you have to go in that direction, so you can take that number and multiply it with W. Then you divide it by the length of W squared. So the one that's down is the one that's down here. The one that's down is the one that is the scalar multiple up here. Okay, so let's do this stepwise. V dot W, we did a second ago. I lost it. But it's 10 plus 24. And then the magnitude of W squared is just 5 squared plus 8 squared without the square root sign. So 10 plus 24 is 34. 5 squared plus 8 squared is 65. So we have the projection of V onto W. Looks like, what did I say, 35 divided by 64 plus 25. What did I say that was, 89? Times the vector 5, 8.
Should be a 34.
Should be a 34
in the
where?
numerator.
In the numerator? Because when you add 0 to anything, you get that anything? Is that the additive element of addition? So you can see it's a scalar multiple of the vector we start with because it's just that piece of it. If you were to lay this vector down on it from its shadow. Okay?
How do we multiply that out, or is that like?
You can just multiply component wise. 5 times 34 is 170 over 89. 8 times 34, 272 over 89. Or somewhere close to that. But you get a vector that is the projection. Okay? All right, so a dot product is a scalar. It can be used to describe work. It can be used to help us find the cosine of an angle between two vectors. And it can be used to find a projection of one vector on the other. And we can also use it to tell whether two vectors are perpendicular to one another. So next time we'll do the cross product. Put a review sheet on Blackboard. Feel free to start it so that if you have any questions, we can take care of that this week. We'll review on Friday, but I can start reviewing whenever you're ready. All right, anybody questions at home? We'll talk about the final when we get closer to the final.
Better idea.